a number of people might be counting on that. And then we'll get started. Okay. Well, hello to my vast audience, and welcome to the last, I guess, session of the Bootcamp this semester. So, a number of, I guess, logistical things to get out of the way. I'll send her a quick an attendance form your way, just so we can have it collected so we know. I'll send that in the chat here, maybe. Chat on Google, and I'll also send it in the Discord, if I can get to there. There we are. Cool. So it's just helpful to have that filled out so we know how many people shipped things. We used it recently, like, for the funding application we just made to get a whole bunch of money into the society. We tell them how many people show up, and the more people show up, and the more we have record of, the more we can convince them to give us their money. And now everyone wants money for fun things. Alright. Cool, and then I'll have a survey thing later. I'll share my screen now. That's probably a good idea, isn't it? Window or screen. Screen 1. There we are. Alright. So, I reckon everyone here's on the Discord, so I'll create a real quick Discord poll, just asking out of the people here, or actually, you know what, you can just tell me in the chat if you'd like, since there's only 2 of you. I'll ask there. I'll just ask, have you taken a look at the challenges yet? And you just say yes or no. And no worries if you have not, because like I said, I put those up quite late today, relatively speaking. Or also, similar question, do you know where to find them? I think, Luke, do you know if you join a session after it starts, if you can see back in the chat history?
Yeah, I don't think you can.
Okay, that's fine. It seems...
Yeah. It's in the Discord though, isn't it? I think, right?
Yeah, in the Discord in here. Cool, and just looking through sounds good. So I guess the idea of today's session was, I'm not sure if we necessarily have time to necessarily go through all of the challenges, but I was going to think of asking you guys which topics you'd like the most revision for, or if you had any particular questions, or if you just had some I'm not sure where to start kind of questions, we could take a look at how to do so. So very, very much guided by you guys. So there's 2 of you that get to dictate the, or 3, if Luke sticks around for long, get to dictate the entirety of the session. So, I think just to get everyone on the same page, I'll go and briefly go over the challenges, I guess, that I've written up. And then you all can let me know which ones you want to look at first. So for Python, I linked this just to the revision, or just to the 2 weeks on that. So those worksheets, that's in the review section. There's something new called list comprehensions, which we'll probably get to take a look at, and I can show off. They're kind of a small new item. There are only a couple new features. It's pretty intuitive, I think, but they're very useful to use. And then a challenge that kind of goes with those is going to be finding a special right triangle. So the idea is that you can use a list comprehension or something like nested for loops to generate a list of, and it, depending on how you do it, could end up to be like 1,000 different triangles, which are just collections of 3 different sides. So something like this, where you have this pair here would mean you have a side of length 3, and one of length 4, and one of length 5. So you would look through all of those, then you would filter them down so that there's only right triangles. So that's ones that abide by Pythagorean theorem, so that's a squared plus b squared equals c squared kind of thing. And so you can just filter them out by that. And then you can find the particular triangle out of that set that has a perimeter of 24. I've got a couple of hints for that. So that's how that first challenge works. Are there any questions about what that challenge looks like, I guess, what the requirements are that anyone has? Off the top of their heads? Or the instructions clear, I guess? Okay, cool. I'll take that as a no questions, at least from Maria. Sounds good. Alright, so we can take a look at that one later, potentially. Or the Arduino one, you might be familiar with. So, a couple of new things there. One is, or the things called switch statements. which we can take a particular look at in a minute or so. And those are just another like alternative to using if blocks, kind of. So you could write if something, then do something, then else in the Arduino language, which is C++. Or if you wanted to do a whole bunch of different things, like say if the number on the number pad pressed was 1, do this thing. If it was 2, do this other thing. 3, do this other thing, and so on for like a large number of values. Switches can be useful, so we can take a look at those. That's the bit of novelty for today. And then also, since we'll be adding digits, so it's like a little pin pad, so if you can imagine you're putting in, say, the unlock code for your phone or something like that. You press a number, and it kind of like pushes all the existing numbers to the left, and then inserts a new number on the right. So there are intuitive ways to do that kind of match with our intuition. Say if you're working on Python, you could have a list of numbers, and you'd be doing dot append 4, so you can stick the 4 on the end. The problem is that that's not terribly efficient. So when you're working with things like Arduinos that aren't quite as powerful computers and languages that are a bit simpler, I guess like C++, or at least lower level, there are some other tricks that are useful to use. So I guess it's good to think about how you could do this mathematically as well. So if you had the number 123 and you wanted to turn it into 1,234, how would you do so, kind of thing? So that's the other new little bit. That's just kind of hinting at it. There's a way to do that numerically. So then the challenge is actually the one that we've seen before. I'm kind of assuming that not too many people have done this one, although I might be wrong. So have any of you gone through and actually finished that pin pad thing from our last Arduino session that controlled the servo motor? I guess I can ask. Nope, okay. I'll start moving to Discord polls because our numbers have grown slightly. Additionally, for those of you who have just joined, I'll resend the attendance sheet if you want to fill yourself in on that. So, there you are. And in the meantime, I'll create a Discord poll. How many of you gave or I guess, finished the pin pad from the Arduino sessions? Cool. Let me get a feel on Discord of how many people did that. I'm assuming that no one has, and that's not because I have little faith, but that's just because like everyone's very busy. So, okay, cool. Yes, it looks like that's the case. In which case, there is that challenge is what I brought that back for today, I guess. So it's finishing this partially complete pin pad that we worked on at some point, and getting it so that it can detect single button presses instead of just a whole bunch of them, because we figured out how to use buttons so they only press once, like a variable. And then you also want to have it keep track of the multi-digit number, so that links into this whole pushing a new digit thing, and you want to be able to actually move the servo. And I have the solution down here if you want to look at that directly, but we can also work through that today. And also, very valid. Yes, if you didn't attend the second Arduino session, that's no worries. So that's all right. If you know a bit of Arduino, I think it'll be all right, and we can go through it all together. It has this partially complete one, and then you can kind of see what needs to be done to get it to the complete version. But if you have questions, that's exactly what this session is for. The last section then is Fusion 360 I've chosen. So the new bit is assembling several parts together. So in addition to actually designing parts, which we did a decent amount of, I think, you can put those parts together into assemblies. So there's a video that tells you how to do that, and there's also a little like mini exercise here. So this one's not directly related to the challenge itself necessarily. But you can use these parts to follow along with this video, kind of, and I'll also demonstrate probably shortly today how you can do these assemblies. Awesome, and here's the challenge itself, which is to design this very gross, complex part. No idea, realistically, what this would be for, but it was on the sheet of exercises, and I think it's a pretty good challenge exercise. The only thing that I had issue with on this is I think, unless someone else can see better than I can, The position of this hole here on the top that's being pointed to by this 10 diameter marker, I don't actually know how far forward and backwards that is. So I had to take a look at their answer key and measure it from there, in which I found it was 30 millimeters from this front face. So I've made a little note of that somewhere. Yeah, here we are. Because I don't think that's actually labeled on there. But aside from that, all the dimensions that you need should be included in this diagram. And you should be able to recreate the part and then look at the answer and see if it weighs the same amount. And that is all for those 3 challenges. So it's designing this part, finishing the pin pad thing, which is this, if you haven't seen it before. That's the complete one. So this idea. And the code that we're writing for this makes it so that you can move this servo. So if I wanted it to go to servo position 0, I could type 0, then hit go to that little number marker, or I could type, 60 degrees, and it would go to 60 degrees. So finishing this project from this template is one of the things we need, or that's a challenge. And the last one, of course, is that Python one, which is to find the particular triangle. Out of all of those, are there any particular questions, I guess, that people have first about what the challenges are themselves? And failing that, which one would you like to look at first, I guess? Because I can help answer questions and then also get you all started on things. And I'll go over the new things, I guess. So what are people feeling first? Is it Arduino, Fusion, or Python? Let me know. Python, okay. 1 vote for Python. What does everyone else think? Fusion, okay. Different votes so far. Maybe what I'll do is I'll create some polls for it. Fusion or Python. Okay. So I'll do Python and also Arduino. Let's try spelling that correctly. Arduino and Fusion. And you can vote for as many as you would like. Fusion. Then we could just go, we'll start with whichever one has the most votes. Hopefully we'll get around to all of them eventually. Okay, cool. Alright, well, it looks from a cursory look, if everyone has done their voting for as many things as they please, we'll start with the Python one, and then, I guess, choose randomly between Arduino and Fusion. And that sounds like a good idea. Okay, cool. So I'll start then by showing off the new feature, because I guess we can probably use that in our Python today, which are list comprehensions. So I'll jump in here. So first thing to ask is, can everyone see this screen decently? Can everyone see and read the code that's here? This code I'm just going to delete. It's just not necessary. Okay, cool. Sounds good. I'll do away with that. Clear the screen. Cool. So list comprehensions look a little bit like for loops, but are kind of squished inside of a list, hence the name, the list comprehension. So to demonstrate what a very, very, very simple one of these would look like is we can create first a list, then you can put some Python expression. So say we wanted to create or list all of the squares up to 100, so all the square numbers. We could take some number, which I'll just call x, and we'll square it. So that's the first thing. But then we need to tell Python, okay, what should x be? So we say, well, do this for x in, and then you tell it what range of values that x can take. So we want to do this for x 1 all the way up through x 10, or x equals 10. So we could do something like range, start at 1, and go up through 10. Now remember, the reason I'm putting in 11 here is because it doesn't actually include this last item in the range. So this will generate the numbers 1 through 10. If I did 1 and 10 like this, it would only give us the numbers 1 through 9. And that's just a kind of quirk of how Python works. So if we go ahead and do this, we can see, well, actually nothing, because I'm not printing this. If I copy this, though, and put it over in the other side, so copy and paste, and right there, you can see we hit 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So those are the first 10 squares, I guess, or perfect squares. So pretty compactly, what this lets us do is simplify, well, lets us simplify much more complex code. So say if we wanted to build this list without using a list comprehension, this is just for comparison, it might look a little bit like, can we include a decimal value in the list? What do you mean? Do you mean like for the range part? Yes, I think that should be possible. I think that should work out all right. Let's take a look. That would just step by a smaller amount, so this should generate a list of 50 items. But it does not like it. Can't be interpreted as an integer. I think... Oh, maybe you can't. Hold on, let's check them. So, we'll get help for range. See if the step has to be an integer. You know, the step might need to be an integer, now that I think about it. Exclusive by step. Okay. It might need to be. So there's a way you can get around that. It's a very good catch, though. So good to ask about that, because that can hopefully be helpful and give you a workaround. So I actually didn't know that range was limited by that. That's just, I guess, so range is probably only for integers. If you want to get around that, you'll have to do a little bit of sneaky mathematics, probably. But you can make this bigger. So say if we wanted to do counting by 10 or 20ths or whatever, or, sorry, fifths. We can make that 5 times bigger, and then over here, we can divide x itself by 5, and that'll give us the same end result of stepping by those smaller amounts. More. Can I get the help to go away? If I run it again, does the help go away? The help is here to stay. Okay, there we are. Maybe I need to copy that, of course. So, copy, and you know what, I'll just print it, actually. Oopsie daisy. On top of our game today. Alright. No, okay, so it's even more upset about that one. And I am not sure why. So, maybe I just upset my REPL. That's entirely possible. Yep, go on. Ah, yes, okay, so it decided to freeze there. So go ahead and run that. Sorry, I don't have... Yeah, okay, so that's fine. So the code itself is fine. My web page died somehow. So here, yes, you can see you get our numbers with each of them squared. So our first one will be 0.2, and 0.2 squared is 0.04. Now you can see here, there's a bunch of weird stuff going on. Like, there's a bunch of zeros and then there's a 1. What's up with that? That's a quirk of computers in general. They can't exactly represent floating point numbers, which are numbers with decimal points. So that's why you see, like here, you have 5 and then just a bunch of repeating 9s. Or you have here a bunch of zeros and a 1. That's because for the computer to perfectly represent every single possible decimal number, it would have to have an infinite number of memory to do so, because just between 0 and 1, there's an infinite number of decimals in between. So they approximate it. So sometimes those approximations are a bit rubbish, like this one, which is off by 3, whatever place down that is. So if you ever see weird numbers like this, don't worry, math isn't broken, just the way computers work. Bit squirrely. For some numbers, though, you can get even numbers, so that's an even 100. But I think this does what we expect it to do, even if it's a bit unpleasant to have to move the step out there. That's something that's a limitation I didn't even know that range had, so thank you for pointing that out. Wonderful. Are there any other more generic questions about, or just anything related to list comprehensions? I'll dive into a couple more of the features in just a second, but anything else off the top of people's heads? Coolsies. Alright. In that case, I think I'll slide on. Yep. Okay. Sounds good. To show off one of the other cool features here. Thank you for reminding me all the time, Google. Alright, so just to make this a bit prettier, I'll say list, and we'll put this all in a variable up above. Oh, okay, sure, that works. There we are. That way we have our comprehension separate from our print statement. Looks a bit nicer on the eyes. Alright, so in addition to their lovely superpower of generating lists really compactly. Oh, right, that's what I was going to do. I was going to show off how you would do this without a list comprehension, so for comparison's sake. So I'll go ahead and comment these out. Don't actually know how to do that quickly, so that's fine. We'll do it manually. So if we wanted to generate the same list of numbers, but without using a list comprehension, it might look... Well, actually, I'll ask the people here. Do people here have an idea of how that might look, since you've all dealt with for loops before? That'll be your main hint, is that somehow it'll involve for loops and building up a list. Any ideas on how we should start our code to generate this, but without a list comprehension? Open to any suggestions. Okay. And if we don't have any suggestions right off the bat, that's alright. I'll get you started. So, generally, one of the more, I guess, annoying kind of parts when you have to build these lists from scratch is you usually start with an empty list. So we'll have our empty list there, and you want to do a for loop, and you build it up gradually. So, say we have 4, and then we can give, and here we can loop through our same range. So at least this part looks almost identical, actually. We can do 4x in range. So you see that's almost a direct copy-paste kind of from the list comprehension. So now we're going to go through and we're just going to list the numbers 1 through 10. So I can show that off and prove that, I guess, by printing them. So if we do this, we get our numbers 1 through 10, just like we expect. Then what we have to do is we have to add them to the list. So we can do list.append to put something at the end of the list. And then we can put our x squared at the end of it, like that. And then, of course, we have to actually print the list afterwards. Hello? Print the list afterwards, like that. And then you see we get the exact same result. But hopefully the key difference that you can see here is this one is 1 line, whereas this one is 3. And this is kind of a nice way of building lists, even when it's just like this. But they also have some other superpowers that I'll show off as well. So, another one of those powers you've got is you can filter items. So, say I only want the odd squares or something like that. So, I can filter for odd numbers. I actually forget off the top of my head if Python has a function for determining if something is odd or even. I don't think it does. But you can find that out pretty easily using the modulo operation. So, first of all, if you want to add a condition to a list comprehension, it's again kind of familiar looking syntax, but maybe in a bit of a different context. So I can write if, and then whatever the condition is, and if the thing is true, it'll get included in the list. So if I only want the odd numbers, then I want numbers, so that I can use my x variable, where when you divide them by 2, the remainder, so remember this gives us the remainder after division, it's the modulo operation. We might not have dealt with that one a whole bunch, but just to remind everyone, if I do 6 modulo 2, the remainder is 0, because it divides evenly 3 times. If I do, say, 2 and 5, then obviously 2 goes into 5 twice with a remainder of 1, so we get 1 back. So basically, when you do modulo 2, this tells you if a number is even or odd, because it tells you if it's divisible or not by 2. So if it's not divisible by 2, which means that it's equal to, there's a remainder of 1, then we know it's an odd number. So this one will give us all of the odd squares. So if we run that again, you see we get 1, which is odd, 9, 25, 49, and 81. Just like that. Now, if we wanted to add it to this list, or this list building operation down here with the for loop, it gets even messier than before. So this here is still 1 line. Granted, it's a somewhat long line, but it's pretty compact. If you wanted to do the exact same thing down here, it gets much more complex. So we would now have to add an if statement in here. So we have to say, if your x is divisible when you divide it by 2, if there's a remainder of 1, then you want to append the thing. So you have to indent that again. So now you've got 3 levels of indentation. You're up to 4 lines total, but I think that should give us the same thing. Yep, yeah. So you can see as these expressions get more complicated, they stay very short, very easy to reason about, whereas the other code starts to get a bit longer and especially stretches out vertically. So that is kind of the core bit of a list comprehension. The last thing I'll point out that's really, really helpful is you can do kind of nested loops with list comprehensions. So I'll show that off with 2 values just so you can all see, because this will be important in the triangle thing we do later on, or perhaps all together, depending on the time we have. Could do it all together. So yeah, so this was fine, great, lovely. In fact, I'm going to do a different list comprehension probably. So let's get all of the combinations of numbers 1 through 3 or something. Or maybe we'll do... Yeah, I guess it depends on what we want to do. We'll start with all just like, say, let's do all combined dice rolls, right? So if you want to know every possible dice roll, if you're rolling 2 dice, each one of them is going to be some number 1 through 6, and you just want all the different combinations. Now, generating all those combinations by hand is a little annoying. I'll demonstrate that here first, actually. So, demonstrate or creating all these combinations by hand, you have to do 2 loops inside of each other. So you could say for, and this would be your dice 1, for dice 1, and then that can be anything between 1 and 6. So remember the end is exclusive there. Then you'd have to do, well, now, okay, for every roll of the first dice, we need to try every roll of the second dice as well. So you end up with something like this. 1 and 7. And then at the very end, inside of here, you can combine, or push rather, I guess, your combined dice rolls. And I'll put those in as a tuple, so it's just a comma separated pair in some parentheses like this, or brackets rather. Just like that. So that will generate all of our possible dice rolls. So if we go ahead and run that, you can see you get, well, that's 1 and a 1, so snake eyes, then a 1 and a 2, 1 and a 3, 1 and a 4, 5, all the way up through 6. Then from there, you start with the first dice being 2, then the second one being all the different values, and you kind of go up like this. So altogether, I think you would get, is it 36 different combinations, I believe, of different ways that you can roll the dice. So that's one way to generate it. It's pretty manual. Yeah, 36 different ways. But this, you can see, it takes, again, 4 lines. You have 2 nested for loops, which is sometimes a bit tricky to reason about. And list comprehensions make this a little bit easier, but again, they stay looking very similar. In fact, you can mostly just take things and put this all in the same line. Like copy this and put it into the list comprehension, and it should work. So to demonstrate that, I'll take this bit here. So we don't need the list append stuff ever, but I can take the dice 1, dice 2, and paste that into the front of our list comprehension, because that's what we want to do, or return at the very end. And we want to do that for every D1 in this range from 1 to 7, and we want to do the exact same thing for the second dice. So we just do for D2 in a range from 1 to 7. And that will work in the exact same way and give us exactly the same thing. So we'll comment out all this code down here. Just like that. And you go ahead and get... Does it not want to run? There we are. Eventually ran. We get the exact same thing. So all of our different possible combinations. So that kind of goes to show how powerful these little list comprehension things are. They can do nested for loops, and also have conditionals, and you can add as many of these as you want, and you can even split them onto separate lines to make them nicer to read, so you could do something like that. And I guess at this point, once you are splitting them onto multiple lines, they do start to look a little bit like for loops, but it's just kind of up to however you want to do it. If you wanted all the combinations that added to 7, for example, how would we change this list? So if we wanted a list of all the possible dice rolls that added to the number 7, what would we add to this list comprehension to filter down so we only get ones that sum to 7? What do people think? Any ideas? I can tell you're all typing furiously. Hey, look at that. Yes, I would agree with you. So, yeah, actually, in fact, that's almost entirely correct. We do indeed start with an if, just like we would do normally. And then you can take, well, I want all things for d1 plus d2 is equal to 7. Except, of course, the caveat here being that when you want to check if two things are equal in Python, you need to use a double equals. But aside from that, absolutely bang on. If we go ahead and try that, now we get just these. You can see, just kind of intuitively, that all of those add to 7. And I think, if I remember correctly, yeah, there are 6 that do so. So, yeah, you have 3 and then another 3. So, 6 items total. Wonderful. So that's the general gist behind list comprehensions. The link that I linked you to also shows you how to do it for dictionaries and sets. We didn't really talk about sets. Sets are just like lists, but the items are unique. So if, for example, sets are defined with these curly braces and then just the items of the set, so if I would put 1, 1, 1, 2, 2, 4, or 5, 5, 5, 4, then it will just end up returning the unique items. So you just get a 1, a 2, a 4, and a 5. And it even actually goes and sorts them for us, which is probably not behavior you should rely on, but is the case in this case. But you can also, yeah, the point being that you can use these same sort of comprehensions to create sets and also dictionaries like we've looked at before. So very, very powerful little hidden bit of Python syntax that makes your code a lot easier to write and a lot less manual, like all of this is. Are there any questions about list comprehensions? I'll do a little poll, see how people are feeling. If you have any questions, feel free to ask. Additionally, since it's a review session, if you have any Python questions at all, feel free to ask. I will be happy to help. Cool, okay. Seems like people are feeling alright about list comprehensions. Got a couple of people who said they're doing alright with it. That's good. Cool. If nobody has any questions, if you do have questions, please continue writing them. But if you don't, then I will move on. Or actually, I'll ask you all what you want to do next. Do you want to go through the rest of the challenge proper on your own, or would you like to go through it together now? We can always bounce between the different subjects, or we can do a bunch of Python at the beginning, whatever people want to do. Yeah, I don't know exactly how to answer that. Don't mind. Okay. Cool. I can recreate our lovely helpful triple poll. So I'll ask again for people who want to keep doing Python, people who want to take a look at the Arduino stuff, and people who want to take a look at the Fusion stuff. And we'll see where we end up. All right. People are excited about Python. Okay. Cool. In which case, then, I reckon we can start with the challenge, take a look at it, and we'll try and work through it together interactively, perhaps. So, we'll address it in stages. So, goodbye, all of our code. You'll be back in a minute. And we'll put this in its own window to the side here. Not quite windows. There you are. Well, it's a lot of windows. That's, which is the right one? This is the right one? That's the right one. Okay. Lovely. So, that worked exactly not how I wanted it to. Wonderful. Point being, once we squish that down to be small enough to fit on the side of that screen, we can take a look at the challenge here again on that side and then write our code. So the first part of the challenge is to use a list comprehension or some other method to list all the possible triangles with integer side lengths of 10 or less. So that means the sides could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units long. You probably can't have triangles with negative side lengths. And we want to generate them as a tuple that stores the size of all three sizes, and that just looks like this, where you've got in brackets size of side A, then side B, then side C, or whatever. And that order is arbitrary. How do people think that we should start? How are we going to generate all of these possible triangles? And we can use list comprehension or loop, whichever people are feeling. Let's see if I can squish this to the side. There. Any ideas? We're kind of generating combinations in a very similar way to like our dice rolling was. So if we saw how we rolled dice with list comprehensions, where we got all the possible combinations, how would we do the exact same thing but just with 3 values? And also partial suggestions are fine too if you don't want to write out full Python code solutions in the Google Meet chat window. I'll give everyone a second more to ponder. Okay, so without any other ideas, we could maybe start with. Yeah, okay, I think that's a good start, Maria. Cool. So we can take our list and we can say that it's equal to, and then put our values in here. One alteration I would make to what you started with there is I would probably put, well, I would put them together in a tuple by surrounding them with brackets. Then I would put, A, B, C. I'll probably use, just because we're dealing with triangles here, and the Pythagorean theorem uses the same letters. But that's the same as your S1, S2, S3. And 4, I would agree. What should we write after our 4? Any ideas from anyone? The crowd goes wild. Cool, okay. So after our 4, here's where we would list the variable that we want to use in our loop or whatever. So we have 3 options here actually. We could do A, B, or C. I'll keep things in alphabetical order, because why not? So I'll do for A, in, and then in is where after that you give the list or collection of things that you want to go through. So say in this case, well, what I want to go through is all of the possible side lengths between 1 and 10, essentially. Because triangles, you can't have a side with 0 length. And you also can't have negative ones, and I said 10 or less. So we'll know then that our range, yes, fantastic, excellent done, Marie. So our range then would be same as we've seen before, which is 1 through 11, which is actually realistically numbers 1 through 10, including the 10. Lovely, okay. Now, what do we do from here? It's pretty similar to what we've already done. We just have to repeat a part of it a couple of times. Any ideas? Okay. So, I would reckon, since we have A dealt with, we should probably think about dealing with B and C in a similar way. And in fact, because of the way that the problem is worded, they'll be dealt with identically. So I'll probably create a new line just so it fits nicely on like our small window here. I'll grab this chunk and I'll put it here once and then down again. And then this time it's for B and this time it's for C. see.
I have a question.
Yes, yeah.
Isn't there a way to like write A for A and B and C, or you have to resolve it each one?
Oh, or do you have to do it for each one? That's a good question. Well, I will see if I can find that out for you real quick. The honest answer is I'm not sure.
Because it's the same condition, so like.
Yeah, it does seem like it's
faster.
yeah, it seems like it's something that should be all together. So, multiple variables same time, maybe. Yeah, it's not something I've seen before, but it's possible that it exists. You can certainly do like several at once. I think that by writing them separately, it like nests the loops, if that makes sense. So you could do a thing where you loop through two like in step with each other. Yeah, I don't unfortunately think. I mean, there is a way that we can, granted, make this slightly simpler. We could put our range in one place, which is actually what I did when I solved it the first time. So I could say the sides are something in this big nest of options, and then we could change all these to sides. Although, unfortunately, that does still keep it a bit like, well, non-optimal, I guess. Well, okay, so one thing that we'll try, but I think this will behave differently. So if we try this, we'll see, and I'll go ahead and print the length of it, because I think this should be 1000. So we can do length of the list. Go ahead and play. Oh, this seems very upset because it's using the internet instead of my computer to run code, which is not great, because my internet connection is a bit sketchy. We'll give her another go, so I'll copy that. Refresh the page. Goodbye, and welcome back. Oh, look, Brooks Rady was editing that. Go figure. Okay. There we are, yeah, okay. So 1,000 options, which is kind of what we would expect, because that's for every 10 first possibilities, there's 10 second possibilities, and then 10 third possibilities, so you end up with 10 times 10 times 10, so 1,000 overall. So that's to be expected. You can sometimes bind multiple variables, like just in general in Python. It's called destructuring, so you could do something like A, comma B equals, and then you could give both of the items here, I think, in a tuple. So you could say that I would want A to be 2 and B to be 6. And then that would work as expected, where A is 2, B is 6. Might maybe work without that, although it might complain. Yeah, okay, might work even without the brackets holding the tuple together. Then our only issue becomes if that loops through them independently or in lockstep, so let's find out. So we have A, B, and C. And that's a very large pop-up, thank you for that. Slide this over a little bit. So I think this probably won't work. This will probably throw us an error because we only have one thing there, and then we can try adding several things. Yeah, so that'll throw us an error. If we try sides 3 times, we have that. I think that might also throw us an error if we don't have brackets around it. Yep, invalid syntax. What if I wrap brackets around it? And then go ahead and do this. Yeah, okay. Too many values to unpack, expected 3. So I think our issue here is that it's, okay, so, I don't know if this actually works. Got it, yes, okay. So it does work, and it also does exactly what I thought it was going to do. So zip is something that we haven't seen before, but it's kind of helpful, maybe. It's another thing that's kind of like from functional programming, which is this different way of thinking about programs, I guess. That's also where list comprehensions come from. I had a whole session originally planned on it, but we didn't have enough time, obviously. So what zip does is it'll stick together 2 lists, item by item. So if I have a list of 1, 2, 3, 4, 5, and I take some, like, I don't know, 5-letter word, hello, and zip them. That was Haskell syntax. Oopsie. Remember when I said it came from a different programming language? Well, I was just trying to write in a different programming language. Okay, so it'll give you some zip object, pretty unhelpful, but you can turn that into a list, and then you can see what it looks like up close. So So there we are. And you can see here it goes through and it connects kind of in little tuples the value 1 and the value h, which is the first letter and first number. And it does the same for the second letter, second number, third letter, third number, and so on. So we could stick things together like that and then break them apart at the end, which is kind of what we've done with sides. If we take a look at our list, you'll see the issue with this. Since zip sticks things together element by element, all of these elements are always going to be the same. So you have 3 10s, 3 9s, 3 8s, 3 7s, kind of like that. So I think, well, I definitely agree, Maria, that it's not ideal, and there might be a way to do it in Python, but I haven't seen one. I do think, unfortunately, there's a little bit of repetition, at least in this chunk of the code, which is a bit ironic, but yeah, unfortunately, I think that's the case. It looks a bit shorter in other languages, but yeah, I think this might be the best we can do. But then again, there are definitely people in the world who are better at Python than I am, and Python changes quite often, so I might add a feature for doing that in the future. But by keeping the separate 4 ends, it makes them loop independently through it. So if here I show off what our list looks like, it's going to be a very long list, 1,000 items. But you can see we still have the last one being 3 10s, but then before that you have 2 10s and a 9, 2 10s and an 8. Obviously if you go up past the 10s, you get different starting numbers like 7 2 2. So, yeah, not ideal, I would agree. But I think keeping them separate like this at least makes them independently loop. The sides variable improves the situation of the repetition, because now if you wanted to change how big all the sides are, you just do it in one place. So thanks for pointing that out, because this is definitely a better way to write it than the way I was writing it. Well, that's a bit hard to see, isn't it? Yeah, see, now we only go up to 5. But yeah, good point. Are there any questions about that, and does that answer, I guess, your question, Maria, even if it's not the answer I'm sure you were looking for?
Yeah, it's fine.
Okay, sounds good. Cool. Alright, in that case, I think the code that we have here satisfies our first condition, which is list all the possible triangles with integer side length 10 or less. I'll change this back to 11. And we get these tuples where each triangle is 3 side lengths. Now, how might we filter this list comprehension to include only right triangles? So we'll add something new to this list comprehension. What should it be? Any ideas? We're looking for right triangles, and remember, we have a rule for right triangles. For all right triangles, well, I'll just pop it up. Pythagorean theorem. For all right triangles, that's not exactly what I wanted to see. I wanted to see the squared version of both sides. And yeah, there we are. That's fine. Sure. Yeah, for all right triangles, a squared plus b squared is equal to c squared. So we can kind of use that rule to select only right triangles out of our big list. So in list comprehension language, how might we write that? Any ideas? Okay, so I think a way that we could try to go about this is by where we've been adding our 4s, we can now add a condition. Yes, exactly. So I think that's exactly the right idea, Maria. I think now, if I recall correctly, Python might be slightly grumpy about the caret sign. Yeah, I think in Haskell works for both languages. I'm always getting turned around with my languages. I think that is a bitwise not in Python. Which is something that we didn't learn about, and that we probably don't need to know a bunch. Bitwise operators are a bit funky. They work on the actual binary number instead of just the regular number that we see. Yeah, or bitwise XOR. Sorry. Yeah, the bitwise not is a squiggly line. So we probably don't want to use that one, but instead exponentiation in Python for whatever reason is just done with 2 multiplication signs. But yeah, exactly the right idea. Yes, and well done. I would agree. So we can do this. We'll do exactly what you said. So a squared plus b squared is equal, with our double equals because we're checking a condition, to c squared. Slide that over slightly. And go ahead and run that. Oh, right, I forgot the if. And no worries, Luke. Good luck with your other meetings. See you around. And here, aha, so now we're down to just 4 triangles. So we're getting kind of close to our one triangle that we want in the end. That's just using a pretty intuitive condition here. You can see, perhaps you can't see right off the bat, but since they follow this property, we know that these are right triangles. But there's also something interesting about these. Are all of these triangles unique? Do we have 4 unique triangles, or is there something different going on here? What do you all think? That was a pretty vaguely worded question, so if there's no immediate answers to that, I'll help out. Okay, cool. So yes, indeed, 2 triangles are the same. I would agree with that. In fact, I think that there are 2 pairs of 2 triangles that are the same. And the reason that they're the same is because even though we've changed the order of these sides, really what that's doing is kind of just rotating the triangle. Yeah, this is what I mean, exactly. So here, these 2 triangles are the same, really, because the 5 is in the same place, which is already similar. But then the 3s and the 4s are just swapped. That's really just rotating this triangle. It's not actually a unique triangle. And then this is the exact same situation, but with these 8s and 6s flipped. So what we can do to find only the unique triangles, there are a number of approaches to this. The approach I'll go with is just a very simple, another if condition. You notice in one of these, the first number is smaller, where you have 3 and then 4, and the other one, the first number is bigger, where you have 4 and then 3. So we can just pick one of those pairs to have, and those are A and B. So we can just say, well, okay, only give me the pairs where A is smaller than B. And then from that, we can get just 2 numbers. Now here, just 2 triangles, and these are our 2 unique ones. So we have our 3, 4, 5 right triangle, and our 6, 8, 10 right triangle. And then we just have one final condition on our 3rd step. Find a triangle with a perimeter of 24. So I'm sure you were all clever enough to actually just count which one of these sums to 24. But if we wanted to filter it out in our list comprehension, what will we do? Very similar to some of the stuff that we've done already. And remember, perimeter is just all the side lengths together. Any idea what we should add here? Right, so it's very similar to some of the things that we've seen before. So say up here where we said, okay, if it follows Pythagorean theorem, here we could just say exactly how you would do so intuitively. If the perimeter, which is A plus B plus C, is equal to 24, then it has a perimeter of 24. So we could just do that exactly as described. So A plus B plus C, is that equal to 24? And we can just ask Python that. And in response, we will get this here, which is our final secret triangle that we're going for. And there it is here, magical triangle. It's a side length of 6 and 8 and 10. So this is the one that we were going for, and you can see we wrote it here with this list comprehension. If we were to write this with for loops and if statements, it would be 6 levels deep, which would look a bit gross. I'll spare actually writing that out, because it would just be a bunch of really nested, indented things, unless one of you really particularly wants to see it. But I think it's something that you could also probably work out on your own. So the advantage of these list comprehensions is that they're really compact ways to write cool stuff like this that helps you generate lots of different possibilities. They're especially good for combinations because of the effect when you have 2 different for loops, how they're kind of nested, and it'll give you all the possible combinations of the 2. Cool. I'll create a Discord poll asking how people are, if people have any questions. Well, if you do have any questions, just go ahead and write them. And I'll ask, are people about comprehensions? And the challenge now. Oops, where's my enter key? There we are. So that is the Python challenge cracked for you all. Cool. Okay. Well, everyone here feeling good about that. That's good. Awesome. Well, in that case, I guess it leaves us with two more things to do. Off the top of my head, would you like to see the new things in both sections? So that way I can actually teach the new things. And then after that, you can pick which challenge we want to work through. Because I don't know if we'll have time for both challenges, but we'll probably have time for one plus going up the new things. Does that sound like a decent plan? Speak now or forever hold your peace, I suppose. Cool. All right. Everyone's holding their peace. Wonderful. In that case, I'll start with the new Arduino stuff. Or I'll start with the Fusion stuff because that has more votes on it. So we'll take a look at how we can assemble things in Fusion. Yes. Good vote for Fusion there, Maria. Okay. In which case, let's do that. So, the challenge for Fusion, which is down here, is to build this whole mess, but the new thing that I'll go over first is assembly, which is slightly different. So we could watch through the video, although I'm sure you are all plenty capable of doing that on your own, so I'll just show off the highlights, I suppose, using the same parts, or challenge, I guess, that they had. So, they have this tripod here. Well, I say here, it's loading. Wow, what a beautiful tripod that they have designed. But there is a problem that we cannot yet see, because we can't actually move things in this version of the model. We'll be able to move them as soon as we open them in Fusion, so open them in Fusion. Yeah, sure, go on. Do what you please. And theoretically that will open in a second, or maybe it will not. We will find out together. Bum, bum, bum. Any opening there, Fusion? Okay, I mean, worst case scenario, we can try downloading it, I guess. Open link. Bum, 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 bum. It's always very reassuring when things work correctly the first time. There we are. Okay. So here is our tripod, which you can see is very similar to that design we were just looking at, but there is an issue with it. That issue is none of this is actually assembled whatsoever. It's just separate parts, all modeled, floating in space. So you can see, obviously, that's a bit unhelpful. And it'd be nice if we could put together this tripod so that it behaves, I guess, more realistically, or as if things are really attached and they don't just pass through each other like they currently do. So that will be what we learn about now. So first we'll put things back in like some semblance of order. And I'll show off how you can assemble items. So first of all, let's pick two parts to put together. Let's say we have this here, which is one of the legs, and then this cap that's supposed to go in the end of it. So of course we could position it very exactly, just like they've done here. And in fact, if we want a really short, like, hacky solution to this, I think we can go ahead and just do as built, and then just select all of the components to connect together. So like I connected those two, for example. So if I were to click OK, now all of these are assembled exactly as they were built, so to say. So it just kind of fixes them together in place. So that's one way to do that. You could also, I think, select all of the items here. And then you can do create rigid group. And what that does is just lock the whole thing together. Constraint select components. Yes, go for it. And I can just click OK. And now from here, you can see the whole thing moves together. It's all one piece. You can't take it apart anymore. However, that's not entirely what we were going for, because like the legs of this tripod, for example, could slide in and out. They're like extending, telescoping things. This little bit up here is a ball in a socket joint, so I could kind of roll around. You have all these different bits of movement that would be possible in the real part that aren't when you just stick it together in this rigid group. But nevertheless, if you're looking for a short hack for doing that, the option up here is rigid group for sticking everything together, and as built joint just sticks things together as you've designed them, I guess. So if we go back, actually, all the way back to the beginning. We can take a look at our separate parts again, and now we can go about attaching them. So we'll here grab this leg and a little cap on the end that we want, and we'll zoom in and we'll focus on just these parts for now. So the first rule when you're dealing with these assemblies is you're going to need to select both parts eventually, but whichever part you select first is the one that's going to move in space. So in this case, for just arbitrarily, I'm going to decide this gray one, or the dark gray pillar bit, is going to stay in place, and I'm going to move this cap into the end of it. So to do so, I want to grab my joint tool, which is up here, but also you can see it has a J as the keyboard shortcut, so I'll just press J on my keyboard, so components have been moved. Do I care? Yeah, sure, whatever, that's fine. And the capture position thing there is just asking if I want to add in this timeline a place for where I moved these components. Oh, and in fact, it's just gone away. You have to select that usually when you want to, say, go and form this joint, because if you click continue, I believe, yeah, it just moves it back to where they were in the beginning. But that's not what we want in this particular case. So here, yep, we'll open our joint with J, capture the position, that's fine. Then you can see now, while we move our cursor, we have this little half moon icon that snaps to different parts, or different places on this part. So it's snapping to the center point of the circle, for example, or to the edge, if I float over the edge. And throughout the center point, there's actually a midpoint there. There's this point here, which is where like this cap end bit is on, or begins, and then there's one for the top as well. So you can see there's all sorts of things to snap on there. In this case, what this half moon is going to do is match up exactly in position with another half moon that gets placed on this object. And this one, you can see the only real nice snapping point is right at the end of the tube, and like way up in the middle. So right at the end. So now we need to think, what on this part do we want to put right on the end of this one? And the answer to that is probably this bit here, this one in the middle, because that's where this little lip kind of starts. So you can see once I select that, it goes clear. And now what I can do is go and select the other half moon bit, which I want to put it there, and it will go ahead and insert the component into place. You can see from here, I can do things like add an offset, so I can get it to wiggle about a little or change degrees. In this particular case, I think that's plenty fine as is, and I'm not too fussed about it being any different. You can also select motion way over here. So rigid just means that things are locked together and there's no motion allowed, and if you animate that, it'll just shake your part for you nice and spastically. There's a revolute, which lets it rotate around the joint origin. So here you can see, well, it's a bit hard to see. The angle thing is kind of the only thing displaying it for us. But this part down here is rotating. You can kind of sort of see the pixels like getting squirrely there. If there were a pattern on this, it would be easier to see. But it's rotating around in that column. Realistically, I think this thing is probably glued in there, so it can say rigid. That's probably fine. And we can just click OK. And from there, you see this rigid joint has been added, which is what that little symbol there is. I think you can hide that potentially, but I'm not entirely sure where you would hide that from. That would probably be under one of these leg things, and I actually don't know what component this is. This is leg 1-3, so yeah, here under joints you can hide the joints if you don't want to see them, but they're kind of helpful to see, so I'll keep them on. But yes, now you see when I grab one of them, the other one moves with it. If I grab the bottom one, top one moves with it, so they're just fixed together as if you welded them. And interestingly, here, that has also applied to all of these other bits. I think that's because this model was initially built with a mirror or something along those lines. So that's why changing this component also changes these ones. But now, let's think, well, what's our next one? It might be nice to have a sliding joint for sliding these in and out of the tripod, right? So we do a very similar process. I'll zoom into the area of interest, which is here. I will grab my joint tool with a J, say, yeah, whatever, capture the position, select the bit we want to move, which is the very end of this tube, and I want to put that against the very end of this one, so you can see it sticks it together. Now, from here, those are just rigidly joined. So if we were to play the motion, you can see nothing exciting happening there. But what we really care about, or what we really want, I guess, from this joint isn't a rigid lock, but something that's a slider. So you can see the different types of things. You have our revolute ones, that was the rotation one we looked at. There's a slider, which slides something in and out on a single axis, which is what we would want. Another one for cylindrical, which allows for sliding and rotating. Pin slot, which allows for something very, very similar. There's planar, which means just two faces have to be touching. And then finally you have a ball in the socket. Yeah, I think a ball in the socket, which we'll have for our very top of the tripod, I think. In this case, we want a slider joint. So we go ahead and do that. You can see, there it is. It's sliding in and out. Now, Fusion's also not immensely clever about how far it should be allowed to slide in and out. So we need to give it some help there. So say under our position, I think we should be able to change the boundaries of the motion. Custom. Yeah, I think it was fine originally. Okay. So I'll have to check how you can constrain their movement distances. Oh, did I just undo that whole joint? I think I did. That's fine. I'll do it real quickly. So J, capture position, click there, put them together, slider joint, and then OK. So now here you can see if I grab it, aha, actually it's moving the whole thing. Very interesting. So that's because the top isn't quite fixed yet. I think that will be fixed once we fix the top. So let's do that first, I guess. So we'll lock that into place. So I'll go ahead and select for this joint. This will just be another rigid one up here. So J, sure. Grab that end and this end here, and put those together this time with a rigid joint. Actually, so that's not even quite correct, is it? Component 2, that's the second one I selected, right? So on the second one, we actually want this end bit to be all the way up here at the top of this collar kind of thing. So, well, that was unexpected. Yeah, because it's 90 degrees rotated, so we can go ahead and rotate that out the other way. So that's, I see what's done there. Intriguing. Why have you done that, Fusion? It's a bit squirrely, isn't it? So we'll go ahead and select that, and then, it's probably because I've selected it from this side, actually, now that I think about it. That makes a lot of sense. If I select it down from this other angle, then it shouldn't misbehave. Yeah, there we are. And that's sliding still, but we want a rigid fixture. So we do OK. Alright, so now we're in the same position where bigger groups of that are moving. So, yeah, we'll just continue on. To assemble bits like this, where it's hard to see what's going on, there's a couple of little tricks you can use. So, say we wanted this red thing to be out of our way. We can click on it. We can see that that's stand 1, or kind of almost stand, not fully spelled. We can just make it invisible by unchecking the eyeball. So we'll do that first. Then we can see here that what is moving, or what needs to be fixed, I guess, is this bar in this slot, which is a bit of a challenging one, actually. So we need to think about how we would properly constrain that. So I think what we should do here is, well, actually, you know what? We can use one of those as-built joints here, because it's going to be a rigid fixture. What we could do is do a fixed joint and then add an offset. But what might be a bit smarter is if we just decided, well, okay, this is correct. Even though, if we're looking at it critically, that's probably not quite correct. There's a bit of an overlap there, like a collision between the parts. If we did just want to assemble them in place like this, then we could take, so I'll take this stand, we'll unfold it a little bit. What is that part? That's just the top part there? Sure. Okay, that works for me. So now we can just take this part and this part, or actually I guess it's this cap, isn't it, that we're assembling together. So we just click all the things that we want to stick together. Although I guess I should be doing components, shouldn't I? So let's see, that's a leg. So that's part of the leg. Bum 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 bum. Guess I can click connect leg, connect leg. So that's all of our legs nice and connected there. And then the connector black. And do that for all of them. Nice, okay. That seems to be correct, even though it's only selected one there, curiously. It's selected all three over here, so now we can go ahead and do our rigid group even. Or an as-built joint's fine. So we can do that. We add these two at a time. Okay, yeah, alright, well, I'm two at a time. So with the as-built joint, then we can click on first component, second component, and then that's done and built. And we can just repeat the same process. Well, actually, we don't need to, sorry, because, of course, this is all mirrored around in triplicate. There's a very strange relationship between these components. I'm not entirely sure how they were originally built, but they are all obviously linked together. If we did want to repeat the action, though, we can right-click, and the top thing in this little wheel that you have is always a repeat the last command, so we can repeat that last command if we wanted to. In the meantime, though, I think what we want to do next is add a rotation joint to our stand, which we hid, which I think is that one? Yeah, that one, there we go. So here, this is a bit trickier. You're thinking, well, what are we really rotating around? We would be rotating around a pin that is currently missing in this hole, but we can assume there's one there. And we can do so by grabbing our joint tool, which is J. We want to grab the thing that we're moving. I guess first we can imagine that we're moving this middle bit. Oh, by the way, very helpful tool, or I guess shortcut, or just keybind, is once you've locked onto like an axis or something, so like this one. So you can see there's an axis there, and you can see inside of it there's another place to get to, but when we try and hover over it, it disappears, and it moves us to this face on the outside. If you hold down the Control button, and I assume it's the Command button on a Mac, then when you move it, you're stuck on that axis. So as I move back and forth now, I can actually select these inside, like, of this cylindrical hole kind of face. So that works pretty decently. Yeah, let's see. If we look at the side, yeah, those are totally flush, so I can go ahead and select on this one. That is our one component, so that's, oh, I managed to select that one there, that's fine. And then we want to select here, yeah, that same group. Click, alright. And that was a rigid joint, which we don't quite want, so we want to revolute. So you can see that spins around there. Now, obviously, that spins too far, but that's alright. We can also rotate it back to being flat, which looks like right about there. We can take a look at this left side. Ooh, dear. To get, for sure, estimate. Yep, that looks totally flat. Awesome. And we can say, okay. And curiously, I guess that's only added it to one of the legs and not all of it, which is a bit intriguing. But that's fine. We can just repeat the same process. So this time I'm going to pull them apart just so I have an easier access to them. Probably definitely should have done that last time. We will go ahead and zoom in and right click and repeat joint. So yep, that's fine. Capture the positions. I want to put that circle there up at, oopsie, up at this inside hole here. There we are. Wonderful, so that's fine and correct. Where does it land? It lands there at the bottom. So again, for some reason that's messing up our angle. We just want to pop it back to, it looks like 20 degrees has been what we've been going with. So we're going to go with 20 degrees and then click OK. Now it's fastened to that. Wonderful. And we'll be able to see this all moving properly hopefully very soon here. I'll repeat the same process here. Right click, repeat joint. Click on that outside face, or outside part of that circle. Come in here, do the same on this inside circle. It moves, it puts it in the wrong place. I say minus 20 degrees, it says okay, and then we click OK. Here we are. So now all those are attached together. Now it's worth, I guess, checking at what point Fusion will let us actually play with this. So it's still moving the whole model around, but that's alright, we can change that in a second, I'm sure. Yeah, so what we eventually want to do is ground something. Yeah, let's pick a component to ground. We'll be there in just a second. So, another thing, actually, that we're looking at now, if we look at this component here, another helpful thing, if you select a part and you press V, it'll hide it, and you press V again to pop it back, so that's changing the visibility of it. So I can select that, make it invisible for a second, and think, okay, I probably want this, for example, to be bound to that. And that is a fine thing to do. It looks a bit silly actually at the moment, as if it should be a bit farther down. Let's see how this will fit on the top. So additionally, if you want to see through a part, but you don't want to totally get rid of it, you can take the part, which in this case is stand 1, I think. Or sorry, no, that's the wrong one. It's STND. And you can right click on it, and you have opacity control. And then you can set how opaque it is, so how much or how clear it is, I guess. So the less opaque, so the lower this percentage, the more like see-through it is. So I'll do 20%, and now you can see, we can see directly through this part, and we can see what's inside of it, which is very helpful. So I'm trying to think about how we want to assemble this, and I think it's fine if we just put it together as is. Again, the video might do this a bit differently, but that's alright. So we'll hide this part for just a moment. That's properly hidden. Then we can go ahead and click, or we'll do an as-built joint. So what was that? Was that Shift-J? Yeah, so Shift-J for an as-built joint, and I'll just click on this component and this one, and that sticks them together just as they are. So now they're a part of one group. And you know what? I feel like this is a good point, or a good component to ground. So when you ground a component, this component is pan, head, cross, whatever this screw thing is. When you ground a component, you pick a part of your design that no longer moves. So in this case, we can right-click and ground is the second option up here. And when we do that, this part, well, everything else moves with it, and it does not seem to be grounded whatsoever. Fascinating. Why is that, my friend? Why do you still move around willy-nilly? Very good question, isn't it? I am not entirely sure why that is still floating around in space and not stuck in one point, but that's alright, I suppose. Yeah, okay. We'll give it a quick check. So, let's see. How to ground and start a component in Fusion 316. 216, that's a bit of a different thing, isn't it? Why does the grounded component move? Ground the component, not the body. Okay, well we can try grounding this other bit inside of it, despite the fact that I still think that's... Oh, or maybe that's an assembly, is what this sign is. Okay, yeah, sorry. So, got it. So I think that if we try grounding this piece, then... no, don't capture the position, actually. If I ground that piece, now is it fixed in place? Yes, okay. That makes marginally more sense. It's a bit counterintuitive. These things here that are made of several little boxes like this are actually assemblies. So these are made of several components, which you can see. So like this leg or whatever is made of the different parts of the leg, which are themselves actually assemblies. So these are nested assemblies. Inside of there you have this actual component. That's the bit that you need to ground. And then inside of components you have bodies, which are the actual 3D modeled things. So bodies are these little cylinders, components are boxes, assemblies are several boxes. That's something that I had forgotten and should not have, but here we are. Anyway, so once the component is grounded, which is this inside bit, so we can actually unground without this outside one, doesn't matter at all. That means it's fixed in space. And what we can do now is move other things. So if we move this, you can see, there it is, rotating, like we told it could. We can also see our sliding in and out. So you see, it still can slide too far. We haven't quite constrained that yet. But you can see it also keeps the right kind of motion when it's going in and out. So it's nice and a slider joint, I guess. And they also will go up and down, which is wonderful. I'll undo all that movement because that's unnecessary. And then you can kind of continue the assembly on with the head. I'll real quickly just jump to the head part because there's a weird, I guess, aspect about that. Or, yeah, okay. So we'll do a couple of things. First we'll just finish the assembly. So don't capture the position. I want to grab this headpiece and I would like to attach that to, well, this other component that I cannot see through you, which is this component. And then I want to make that rigid, sure. Bring you back into visibility. Where's it gone? Hello? Oh, I see. Have I made the body inside invisible? Nope. What bit have I made invisible? Oh, all the way down on that component. Okay. Opacity control, you can be back to totally opaque. That's fine. But yet you are not. Okay, yeah, so the hierarchy of these things is a bit confusing, I think. Because if the top bit is clear, it doesn't matter what the bottom bits are. We'll just make them kind of clear. Okay, that makes sense. Enough. So the red bit's fixed now. This is still our only totally unattached part. Well, this and its friends. So actually, that and its friends I think I'll create a rigid group out of, because I think none of those should be moving separately. So that is the stand for camera bit, as well as the pin or screw, whatever this piece here is. Let's see what that is. That is this HUD thing. Okay, so we'll select that, as well as the stand for the camera. Oh, is that going to select that against my will? No, it's not. Okay, there we are. So that whole bunch there, we want to create a rigid group out of that. And also, by the way, all these things you can look up with your S tool key, I think. So, rigid group. Those 6 selected, fine, good, great. And I can click OK. So now, there we are. This whole thing is one big rigid assembly. And we can apply one last little constraint for this ball movement here. So Fusion actually has something for these little sockets. So it's a bit of a tricky one, so we'll see if I can figure it out. So if I flip up our joint thing with J, capture position, fine, whatever. Then I want to grab, say, the center of this ball, which is there, and I want to get somehow now to the center of this sphere area, which you can see if I roll over the inside face, it highlights it for me. So I can go ahead and click on that, goes ahead and moves it in. So there, you can see it's on its revolute constraint, which isn't terrible actually, because it does revolve a little bit this way. But it also can go a bit side to side. Well, actually, maybe not in this particular design, if I'm being honest with you. It might just be a revolute kind of thing like that. If it were a more proper ball joint, you could do the ball constraint here, and you can see that kind of like moves all around. So if I built it like that, I could grab it, and it goes left and right and forwards and back. So this particular design actually isn't meant to do that, despite the fact it has a ball there. But that is just another type of constraint that you can use when you're assembling things. So that was quite a bit of blabbering at you. Do people have questions about how assemblies in Fusion work? In fact, that took much longer than I was intending it to. Probably because I did not practice enough. So I'll ask about how people feel about this. So. Assemblies in Fusion. Cool. Are there any questions? The poll has gone very lukewarm. Nobody knows how they feel. That's right. I don't know how I feel either. One person likes Fusion assemblies. And if you ever, by the way, want to like unmute your microphone and ask questions, that's definitely also allowed at any time, if it's easier than typing for people. Okay, cool. And I think that video that I linked will have even some more advanced tricks in it for assembling things. If that video doesn't have like limiting constraints, I'll be sure to include that one or a video that talks about how you can do that in our document for today, because the same channel that did the nice Fusion like beginner tutorials also explains that at some point. Cool. All right. Are there... Okay, so I guess we'll take a look at what we have left to do. We have left the new bit for Arduino, which I'll probably go over really quick, and I think I'll just explain it more than anything else, as opposed to like demonstrating it, because it's a bit time-consuming to demonstrate. And then from there, I'll ask what you guys want to finish the session with, if you have any questions about the Arduino one or the Fusion one, in terms of like designing this part, because this is a pretty complex part. It took me a little while, but it's with all stuff that we've been taught. And then extending this challenge, a bit tricky, but I'll show you the new bits that might help. So yeah, real quickly, I'll go over these new chunks, which are just the switch statements and then how you can pull this off mathematically. And then I'll ask what people want to do next, and we'll end the session on that. So real quick, we'll just take a look at this link that I've linked you to. Yeah, sure, take my cookies. And we see C++ switch statements. So here they've given us the general structure of these sorts of things. They've written switch, and then here's your some value. And then here is, well, if the value is equal to x, or if the value is equal to y, then you do something, and then you break once you're done. If you don't include this break, it'll do all the things beneath it. We'll see if we have a nice demonstration of that here. So yeah, here's one for day. So ignore these lines here. That's not something that'll work in Arduino. This is one of the places where Arduino's language diverges from C++. That's how you would print something to the screen. So this is the equivalent of like Python print Monday. In Arduino, it would be serial.println Monday. But it does show off how these things work in general. The idea being that instead of having one if statement that says if day equals 1, then print Monday, and then having a second if statement that is if day equals 2, then print Tuesday, which would take ages. You can instead have just these conditions where you say, okay, the value I'm checking is going to be day, so that's why day is here in the switch part, and then you have beneath it all the different possibilities. So if the day is 1, then you run this code, and break means you stop running code. So it'll print Monday, and then it will be done with the whole switch, and it moves to the outside of the switch, which is out here. So in this particular case, like it just told us, if we have day 4, it's going to take a look at case 1. So it's going to say day is not 1, so we're not going to run this code. So it can look at case 2. Well, day is not 2, so it won't run that. Day is not 3, so it skips that. And then it gets, aha, day is equal to 4, so it will go then and print out Thursday. And then it will hit break, and it will quit, which is how you can get this. Break keyword, let's see if that explains that. Okay, so that's just... Okay, there's a default, which is fine and good. And I don't think it'll... Yeah, it's even got some exercises for us. Sure, we'll go through those. That's easy enough. So I'll have to show you at some point what happens when you don't use the break. Yeah, there's a couple of ways we could do that, actually. You know what? Let's play with it. We could click the try it itself there, but I'm not particularly feeling that website's interface. So we can do Replit. Has a nice interactive way to do a whole bunch of things. So we can do C++. Sure, zigzag fitting programming language. Whatever you think is appropriate, REPL. Alright, here we are. There's our code. This looks different from how our Arduino looks. I wouldn't panic too much about that. That's just because it's a different environment. I did mean that, and I did definitely also forget how to fix that in C++ because I don't actually program in C++, so instead we'll just follow its suggestion. Doop and doop. So if we go ahead and run this, takes a second, then we can see it's printing looking forward to the weekend. Now the reason it's done that is because it's taken day, which in this case is equal to 4, taken a look at the switch, and then it's not checked the cases, so it's not equal to 6, and it's not equal to 7, so then it runs this default case. So you can have this default is a special case that'll run if all of your other cases fail to run. If we change this to 6, then you can see that today is Saturday, because it reaches this first case and then prints out today is Saturday, then breaks and quits the switch. However, If you don't include this break, and this can either be a weird, useful thing, or it can really mess up your day. It's messed up my day before. If you don't include the break, it will continue to run all of the cases below it until it encounters a break. So here it will print first, today is Saturday, but then it will also print, today is Sunday. And it's printed that today is Sunday because we haven't put a break between these cases. In fact, if I remove this break, it'll go ahead and print all three things whenever we have the first one. So it'll say today is Saturday, today is Sunday, and looking forward to the weekend. And if we started at 7, it still falls through, but it'll just start at the second one. So it now starts at just today is Sunday, and then it also prints looking forward to the weekend. So that's just something to keep in mind. And I'll show real quickly how those are used in the actual bit of code they'll be asking you to write. That's the wrong window entirely. That's why that's a bit confusing, isn't it? Boop, boop, boop. There we are. There's where Replit went. So here, where I'm using that in my example of the solves code is I have a switch here where, and in fact, I could improve this code for sure. Yeah, in fact, let's improve it together. Okay, so first of all, can people see this, or is this very, very small? It seems a bit tiny on my end, so I'll try and make it a bit bigger for you. Is that visible enough, this switch statement chunk? Okay, awesome. So what I was doing here was, if the button press I detected was less than 9, so if it was something 0 through 8, then I would treat it as just a digit, so a number, and then I would call my push digit function I defined elsewhere. Otherwise, I would run this switch. Now, in hindsight, that's a bit silly to use this if out here and then an else here. We could do this whole thing with a singular switch. So the way we can do that. So first of all, I guess we'll check. That's the full screen. Hello, full screen, please. We'll test the code real quick. So I'll go, well, we know it's working, right, because I ran this earlier. So I type 0, go 2, goes to 0. If I type 70, it'll go all the way out to 70-ish. Maybe, unless it's running too slow. Yeah, there we go. But it'll work the exact same way. Well, actually, can someone see? So here I have 3 specific cases that I care about, but then I have a sort of like all of the other cases sort of thing. How could I improve this chunk of code based on, or versus what I've already done? Any ideas? Based on what we've taken a look at with switches? Okay, so I think the trick here is when we have something that we always want to do when all the other cases fail, that's a perfect application of the default case. So what I can do is, and actually here you can see there's no break between these two cases. That's intentional because whether or not you've pressed the clear button, which is 9, I believe, in this particular case. Yeah, because I'm treating that as the clear button. Or this as the enter button, which is 11. Regardless of which one you click, you want to reset the total to 0 at the end. So this actually ensures that even if you're in case 11, it falls through to case 9 and runs that one as well. After this one, though, we will want to break. We don't want things going after that. And then here we can add our default case. You can say default, and then we can tell what to do in the default case. And in this case, that's going to be to push the digit of the button. Let's try and select that correctly, shall we? Like that. And then we can entirely get rid of this whole if statement, this whole else, and unindent this. And I don't know if it's going to let me do this. Hey, it does. How nice. Oh no, that broke everything. And then we'll have to re-indent these things here. Wow, this is some funky indentation. That's alright. Not my problem at the moment. Whereas Python is very picky about indentation, C++ kind of couldn't care less. As long as you remember all your semicolons and curly braces. So let's give this a run, see if it throws out any errors at me. Nope, seems to work fine. And we'll double check. So if we're currently at, I think, 90 degrees, so I put 0 and then go, goes to 0, 60, it'll go. And actually the serial monitor, I forgot, I programmed it so it shows you what you're typing. So if I type 1, 2, 3, you can see 123, I can press go. Or I can use my other button, which we just programmed. If I do say 70 degrees. Oop, so 70 degrees. If I want to clear that, I can press this clear button here. That still works correctly. Wonderful. Okay, so that's how switch statements work. We've even managed to improve my code because I'd forgotten about the default case. See, everyone can always improve. Awesome. I'll ask then if there are questions about that. Real quick, actually, let's take a look at how I'm doing the digit thing. A very simple mathematical trick. If you want to push a digit in the ones place, multiply everything by 10, then add the digit you want to add. I'll show you how this works with a calculator, although I'm sure you can see it intuitively. So say you have 1, 2, and you want to add the digit 3 to the end. Well, you can't just add 3, because then that's 12 plus 3, and you're going to get 15. That's not what you want. What you want to do is just add it in the ones place, but shift everything over. Now, a way to shift everything over mathematically, of course, is just to do a multiplication. So by 10, since we use base 10 number system. So if we take 12 times 10, then you can see it basically shifts it over, leaving a 0 in the ones place, so you get 120. And then to this, we can add our 3 value. Then you get your 1, 2, 3. So that's our cute little mathematical trick that we're using here. We're taking the current total, which is the number that we're keeping track of, multiplying it and setting it equal, or multiplying it and then setting it back equal to itself times 10. Sorry, that's not very clear, is it? So the times equals and the plus equals are exactly like in Python, where it's an equivalent statement to saying total is equal to total times 10. So it just does the multiplication and the assignment in one step. So these are identical lines, or identical bits of code. Wonderful. And then obviously it just adds the digit on the end. So that's how that works. That's that new bit. Okay. I think that was all of the novel stuff I wanted to talk about today. So I'll ask if there are any questions, and then the last 15 minutes are up to you guys, what we do. So I'll ask about switch statements and the digit pushing trick. Cool. Poll is up. Awesome. With that, I got 2 people on board. Okay, cool. Awesome. Are there any questions? Hey, all 3 people on board. Wonderful. Cool. In that case, I guess it comes down to what we want to do last. I realistically don't think we'll have quite enough time to actually finish either of these ones, unless people want to stay for longer than normal, but I don't want to force you to do that. So, which bit would you like to take a little bit of a look at, or do you have, like, any questions regarding the entire year, or even things that we didn't do? In fact, if you want, we can use this as like a workshop time for telling me what you want to do in the second year, or second semester rather, because we're thinking more advanced kind of sessions then. I can even send you this survey early. So I'll send out a survey early. And then I will create a quick poll here to see what we do right now, which is just, should we start a challenge, or are there questions / feedback? And we'll say for challenge. I realized that I phrased a like multiple choice question on a yes/no poll system, so it was a bit confusing. So the thumbs up for once you get there is for doing a challenge now versus just vibing about. Cool, one person wants to do a challenge at least, which is cool. If we do the challenge, I'll have to ask which one, so we'll say Arduino or the Fusion one. Seems like generally there's been slightly more interested in the Fusion one, so I guess we'll see what people think now. I'll give everyone a second to fill out like the survey if that is what you were doing. So I won't rush you. A bit about class function. Oh, so do you mean like how classes work in C++ or Python? And do you mean like classes in a object-oriented programming language? I guess also is good to ask. I could definitely show them off in Python. I'm thinking that might be what you're thinking of. Okay. I don't know the difference between the Python and yeah, so it's basically the same idea between Python and C++. There's a bit of or the Arduino one. They're very, very similar in terms of like the concept behind them. They're just written differently because they're different languages. But yeah, I think I'll probably show off then the Python one since I reckon that's easier to do like, or to understand because just Python in general is kind of nicer on the eyes. So, in fact, there was yet another session prepared for this one, so I can go and take a look at what I had planned for that one. Oops, not the about. But we can take a look at Python, look at all the things tagged Python. We got a syllabus here that we didn't quite get all the way through. We will soon. Functional programming, last one. And the whole third session was meant to be object-oriented stuff, which is stuff like about classes. So we'll do that little exercise that we have listed there. Squish it on over. Cool. So we want a new class then called vehicle. I wish you would not be like that sometimes, Windows. Okay, there we are. That's fine. So classes are kind of like, well, they're blueprints for objects, and that's where the object-oriented programming thing comes from. And objects are groups of data with functions. So maybe that's what you mean by a class function, or maybe you just mean the function of classes in general. Regardless, I'm trying to explain both. Functions inside of these objects are called methods, actually. So that's a tiny terminology difference, but people will understand you obviously either way. So in Python, if you want to create a new one of these classes, which is a blueprint for, in this case, vehicles, so we'll create a vehicle blueprint, you just start with the keyword class. Then you give the name of the class that you want to define the blueprint for. So in this case, that's going to be vehicle. Note in Python, we usually start these with a capital letter, but that's just convention. Then you have a colon, and then the next line. And then inside, you just put all of the associated things. So, yeah, the most important part of a class is probably its constructor. So a constructor is a function that creates this object from the blueprint. So in this case, what we will do is, we'll follow these instructions here. So we'll create a constructor. Constructors are written a little bit of a strange way. So when you're defining methods, these functions inside of classes, they start just like regular functions do with def. But then the constructor has a very special name. It has 2 underscores on either side. So underscore underscore init, and then underscore underscore again. And that is a constructor. And you can see here it kind of gives us a little template that we could use if we wanted. Well, not that clicking on it would do so. And all of these methods take a special parameter called self, which refers to the object being created or being operated on. And then you can take any number of other things just like a normal function would. In this case, I'm taking a name, a capacity for fuel, a speed, and then optionally taking miles per gallon, or for like the fuel economy, or I guess that would be liters per kilometer, depending on where. But that one is optional. I don't actually know if we got around to showing off optional arguments. We might have. It was definitely in the worksheets. I don't know if we got to it in our live sessions. But you can say, in the argument list, you can give it a default value. So I said the default should be 30. So when we do that, it means we don't have to give the thing when we don't have to give the miles per gallon explicitly when we create the object. And if we don't, it'll default to 30. And then inside, you set these instance variables. So self, you can think of, this is the object. Self, by the way, is just it's an arbitrary name. However, it's a very commonly used arbitrary name, so I would try and stick to using self for this kind of like purpose as your first argument, because it refers back to the object, so it's back to itself, kind of. So inside of the self, you can do self dot, and then you can set values inside of it. So if I want the model to be equal to the model name, then I can do the, and this is just following my little specification that I wrote out at some other point. In fact, I have the fully written solution for this entire challenge, just on a different operating system. I promise I have a girlfriend. She just goes to a different school. Fuel capacity, there we are, and then self dot speed is just equal to speed. So note here that self.speed and speed are actually different things. Speed is this argument here. Self.speed is some piece of data that we're storing inside of this object. And you can store it inside of the object by doing the dot and then the name. So speed, and then same for the miles per gallon. And then there's also some empty ones that we're setting, which is the odometer. This was quite a complex exercise that I prepared, wasn't it? Probably going a bit overboard here. An odometer starts at 0, that's fine. And fuel should initially equal fuel capacity. Okay, so we can have our fuel is equal to the fuel capacity initially. Let's try spelling fuel correctly. Or actually, it was just cap, wasn't it? Lovely. So, well, it sounds like the people above me are bowling. That's fine. So we can try and build this object now. When you're using this constructor, when you're calling it, it actually doesn't look like, you'll never see this underscore init function. When you're creating a new thing from this blueprint, you just give the name of the blueprint, which in this case is vehicle. So you give the name of the blueprint. And then inside of here, just like a regular function, you give it its arguments. So I could say, what model is it? Maybe it's a Leaf, a Nissan Leaf, one of those electric ones that buzzes around campus. So we can have a Leaf, and its capacity, I guess it's technically an electric car, so I don't know, some arbitrary number, we'll say 40 units of something, maybe kilowatt hours. And then the speed, maybe it can go, I don't know, about 90 miles an hour. And then the miles per gallon, I'll leave off for now. So if I create that, of course, I have to run this code first, that's my bad. Oop, or not, it has destroyed my thing that I typed there. Fine then, that's a bit rude, okay. We'll retype it really quickly. If, and we have 40, and the speed was 90. And that is all we need for now. So I run that. There you go. So you see it returns as vehicle object, it says. Now if I put that in a variable, we can inspect it some more. So our car variable looks like. So we have our car. Now say we want to know a little bit about it. We could say, we can, just like we use self dot over here, we can now use car, because that's the variable, that's the object, dot model. So this will tell us what model it is. So it's a Leaf. And say we want to know how fast it is, we can get its speed. And if we wanted something like the odometer, that's going to be initially set to 0. So we can see 0. Miles per gallon, note that we didn't specify that, so it fell back to the default of 30. So we have miles per gallon. Although that doesn't make much sense for an electric car, but I did not consider that. Okay, and then what you can do basically here, so you do, I think that's a partially complete question, so I will let you finish the question. And I'll show the pay attention to it, and in the meantime I'll show what another method looks like, I guess. So, we'll have 5 distance. So you don't call the method name. Not with the constructor, because it's a special one. You do, in this case, so I'll show that off real quickly, because that is, you are correct, you do call it by the method name. Init is just one of the special ones, so you construct it just with the capital name of the class. But drive, for example, here, and I'll also put my self variable, and go ahead and put this on here. So driving, we'll say, I don't know, we'll print a message saying with our f strings, I don't remember if I showed off f strings. Please don't be so squirrely, Python. Oh, it really doesn't want me to use single quotes. That's fine. We'll use double quotes. It doesn't like any quotes for that matter. Okay. No matter. Alright, there we go, that's fine. Drove, dist, miles. So we can do something like that. And we also say at the speed. At, and then we can give the speed in these brackets here, which is self.speed, because we've stored it in the self object, and that is miles per hour, I guess. So we can run this. Actually, I'm going to copy this one real quick here. Copy, or even I can take this whole chunk here. Oh, that's not even something I can fully copy. That's fine. And we'll put it at the end outside this class. I also realize we're at time, so I'll finish this up here. 90 and close. And go ahead and run. Now if we take our car, you can still see things like the model. But exactly, you're correct about classes with methods. Here, if I want to drive the car, then I do call it with the name that I've defined after the def, and I also need brackets. You always need the brackets, even if you have no other arguments. Self is automatically passed to it, so you don't need to pass anything for self. That is what this is. The car is itself. What you need to pass to it here is just a distance, so I'll say 30 miles, and we run that, and we can see drove 30 miles at 90 miles per hour. And if you're wondering where the 90 came from, that's of course just because our car's speed is equal to 90 miles an hour. That would be driving perhaps a little fast, even for a motorway, but you know, maybe these people like to live excitedly. Do you have any questions about that? I realize there might be probably a lot of questions. There's a lot of stuff going on with object-oriented programming. If you want, you can take a look at this like syllabus page, and all of number 3 kind of talks about, it's a general outline of like different things. So these are maybe things that you could Google if you're curious about them. And if you Google these things, I'm sure you'll find some useful information about each of those topics. And then hopefully next semester or sometime, I'll actually have more nice worksheets for this. So I'll link you to this just in case. It's on the website. I'm sure you can find it, but in case you can't, there you are. Lovely. We are at time, but if there are any questions, I'm still here to answer them. Does anyone have any final questions? Sorry I couldn't dedicate more time to this last little object-oriented bit. It's definitely very, very, very useful. But yeah, it's just something we haven't gotten around to yet. Cool. I'll overall ask then, we'll do a poll. Are there any final questions? So this is one to answer. If you don't have a question, I guess is the thumbs down one. Sorry for flipping it on you. Cool. And then aside from that, I'm sure people, at least one person has already responded to the form. If another person wants to, because I realize I might have rushed you through it originally. Here's that. Yes, within the Python code for the Maya band, actuators, etc., you're using a bunch of classes, right? Yes, yeah. So, right, for those of you who are not interested in learning about the classes, I will free you to have a lovely day, and thank you for coming so much to the bootcamp sessions. Next week on Wednesday, the exact same time, will be the big showcase. No one particularly wanted to show off anything. I don't blame you. I mean, you've just been learning things anyways. But everyone did want to see what the other part of the team has been doing, so they're going to all come with fun stuff to show off from ARM, LEG, and BCI to show off to everyone. And that's just, I mean, I'm sure you guys have, or a number of you, I know a number of you have already been working on those teams as well. But that's also a fun thing. Showcase and social, same time next week. But if you are interested in the MyMan thing, I'll real quickly dive into that, because I've actually written a bit of code about that. So here, of course, on the GitLab, which is redirecting me to very slowly, sign in with whatever password it remembers. I have far too many things. Arms and Glory. There we are. Sheffield Bionics. So this is what me and Thomas did over the summer in terms of classifying EMG data. It worked like surprisingly well. So we can put a band on your arm and you can move your hand and the program can figure out what shape your hand is in sometimes, or like what gestures you're doing. And it's pretty decent at it. Of course there are quirks to work out, but it works pretty well. So here's a bunch of Python stuff. collection. That's one working with the Myo band. So yes, you're right. So what we're doing here, when you have a name between brackets in this class part, that's something called inheritance. It's a bit complex, but it basically means that this Myo raw is also a class. In fact, this class is, I think, in our repository somewhere, because I had to update the code for it, yeah. By the way, if you want to use the Myo band code with Python 3, this version in this repository works with Python 3. The default library does not. I just made some small tweaks to it. So if you want, I'll obviously link you to this, should you be curious. Thanks for that. But yeah, so this is the code that I did not write. This is the Myo library. So like here's the Myo raw or whatever. So here you can see somewhere in this massive file, there's going to be a class for Myo raw. There's a class for Bluetooth stuff. Yeah, you're right. This makes incredibly heavy use of classes. Everything they've put in classes. Let's see if I can find Myo raw. Yeah, there we are. So here's the thing that we're inheriting from. That's an old relic. You don't need to do that in Python 3. Sometimes in Python 2 you used to need to do that. This is some very, very old code. But you can see here, here's the constructor. So when you construct it, it tries detecting if the dongle can be found. So it'll throw an error if it can't find the dongle. Sets a number of variables. So you've got these handlers here, which are just empty lists for the time being. No connection yet. The self Bluetooth is an object in itself. So that's the Bluetooth object that we defined up here, the BT object. And you can see here are some more like different methods that run on it. So like .connect is actually something we'll be using. So you can see this has a whole bunch of code inside of it for connecting to the Myo band. And that gets run when we call in our collection code, which is here. That gets run when we call self.connect. So because we are inheriting from Myo raw by doing this, we get in our class all of its data, all of its methods. We can just use them as if they're our own. So note that when I'm calling self.connect here, this class does not actually define connect, I don't think. So we have init, we have pause, next repeat, next gesture, empty handler, new handler, write data. Yeah, but you can see in this whole object or class, there's not a .connect. That's because the .connect comes from Myo raw. But I can use it with self dot as if it's my own because we inherited from it this way. So that's kind of how inheritance sort of works. A bit tricky to get your heads around sometimes, or head around sometimes. But yes, I definitely agree. The Myo band makes very, very heavy use of these class things, but they're nice to work with. So you can see here, I define this class then in the actual main part of the code, which is down here. We're creating that new class. So here I am creating it, and you can see between these, or between the brackets here, there is an argument to the constructor. So that goes into this TTY variable, which is one that has a default, so note that it doesn't have to be supplied. And then I am listening for a bunch of keys on the keyboard, and I can check if it's paused or if it's updated, and I can write data. So these ones here without the parentheses are variables. So im.updated, that's a variable. You can see self.updated here. So that tells me if it's updated the data already. And then if I want to call one of the methods, I just do the same dot, the name of the method after the def, and then even empty brackets. Even if you don't need any arguments, you still need these brackets to tell it it's a method, not a variable. So that's a variable because there are no brackets. This one's a function because there are brackets. And this write data obviously just calls this whole write data method. Does that clear things up a little bit there for working with the Myo band? A bit. This is a maybe helpful model to work off of if you're wanting to ever do things with that. And if you're ever feeling like you want to expose yourself to more trauma that was the Git session, I recognize that was probably the most difficult session. So I'm going to try and work on explaining Git better in the future. But it's all in the Git repository, so you can download it and clone it and play with it and make any tweaks that you want with it. And it's part of the Sheffield Bionics organization, so you can do that. Awesome. Are there any other questions? Anything at all? I wish Google would tell you when people are typing. I never know. Okay, cool. Well, No worries. Do you know which bit that you might have missed, or do you mean just now when I'm like pausing? I asked if there were any more questions, is all. And if there are no more questions, then I will release you all to have lovely evenings. Yeah. No. Okay. Is that mean the? Okay. Yeah. No. No questions. Sorry, I'm not entirely sure what you mean. Okay. Awesome. Thank you. Happy to help. Cool. Awesome. If that is all, then thank you for coming along. Yeah, very happy to help. Thank you both for coming. See you around. See you next week at the showcase. See you.